Hi, so we're going to do a mini movie on two mean tests, hopefully reviewing some of the things we've already talked about so that you can make sure you understand it before we move on. Alright, so we're going to talk a little bit about two mean tests, and I just want to kind of review why we might be interested in a two mean test so it'll help you maybe pick out which ones really are two means. So we're talking about comparing two things. I like to think of it as looking at whether or not it's new and improved or even if it's worth more money. So I've got two examples here. We're trying to figure out if there's a difference between fertilizer A and fertilizer B. Now, one thing that we know is that we're pretty sure we're not going to get the sample average from A and B to equal each other. I mean, it's just really unlikely. But the question is, depending upon how close they are, can we actually say that the true means are equal to each other? Or is it going to be one of those situations where we can go ahead and say they're not equal to each other and then conclude that there actually is some improvement in going to fertilizer B? So again, another choice would be fuel 1 versus fuel 2. The idea here is this one is supposed to have better gas mileage, but it costs more. And the question is, when we take and actually do the experiment and figure out what the sample averages are for 1 versus 2, we're likely not going to get those to equal each other. But the question is whether or not the true means are actually equal to each other. And in this case, what we might end up finding is that they are equal to each other, and then basically we're wasting our money on spending more money for something that's more expensive if it's not actually better. So I found this, and I thought it was kind of interesting to kind of get an idea of what we're talking about. Don't forget that the true mean of the population is related to this distribution that we would expect to get. And in this case, we're taking the true mean of the population and then going ahead and taking a number of samples, and then we're going to, this is the sampling distribution of the average of X. So this is an example where the true underlying population distribution is in fact normal, and that also means, but even if it wasn't normal, we would still expect the sampling distribution of X bar to be normal. Okay, so if we consider what the two true mean population distributions of our X bar are, we can go ahead and take the difference between the two, and we're going to get another distribution where the center is going to be the difference between the two mu's. So this is the reason why when we have our null hypothesis, what we're actually going to consider is mu1 minus mu2, and we're going to have it set equal to delta, which is going to be what we think the difference is between the two. Alright, so what is that true two mean null hypothesis is always going to be that mu1 minus mu2 equals delta. Hopefully that last picture kind of shows you why we're going to use that terminology in terms of the distribution that we're looking at is actually the difference between mu1 and mu2. So what is delta? Well, delta is our guess for what we think the true difference of the two means is. And typically delta is going to equal 0. And when it does, it's almost the same as saying that your null hypothesis is that mu is equal to mu2, which is perfectly valid as well. I just want to make sure that you understand that this is definitely valid, and that's where it comes right out of the distribution for the difference between the two means, whereas this one is a simplified version of what we're trying to prove. Alright, so I just put this together to kind of help remind us in terms of thinking about a little SAT question. One mean is to mu, which is our guess of what the true mean population is, as two mean is to delta, which is our guess about what the difference is between the two true mean averages. Let's talk about some examples. I'm going to go ahead and use two clinical studies. In the first study, we're actually looking at a cholesterol lowering drug. Okay, and in this case what we're going to do is we're going to have 40 patients on the drug and call that 1. We're going to have 40 patients on a sugar pill and call that 2. So this sugar pill is going to be sort of like our control. We're going to see what happens to the cholesterol when there actually isn't any drug involved. Okay, as a result we're going to end up with 80 patients and 80 data points. Okay, this means that we're dealing with an unpaired example. We have a data point for every single patient. We're not collecting more than one data point from patients. Okay, and the little clip art that I picked was, please be on the lookout for these socks. These socks are missing. So these are unpaired socks. So another example would be something like weight loss. Now in weight loss we might go ahead and do the same thing and take 40 people and then 40 different people, but really that doesn't make sense because what we really want to see is whether or not they lost weight. So we're going to go ahead and take 40 patients and we're going to weigh them before, and then we're going to have 40 patients and weigh them after. As a result, what we end up with is 40 patients and 80 data points. So 80 data points is going to tell us that it's actually paired. Okay, so this is really your big clue. 80 patients, 80 data points, unpaired. 40 patients, 80 data points, paired. And what ends up happening is, in this case, we care more about the difference between the two than the difference between the two averages. All right, so what happens if we have this one over here? Again, we know that when we take the data, we're probably not going to get X bars that equal each other. But the question is, do the true means actually equal each other, or could they? So that's all we can do, is kind of take a guess and see whether the evidence is going to point in that direction. So if we want to test this, we're going to go ahead and use that null hypothesis that we talked about. Mu1 minus mu2 equals a delta, and in this case we're going to set the data delta equal to 0. So we're just looking to see if they're different or not. Now from this test we're going to be able to conclude whether they're equal or whether they're not equal. Now at the same time, we could do a one-sided study, but I'm just keeping this example to a two-sided study. Okay, so what does it look like over here? Well, again, we probably know that we're not going to get an average A and an average B that actually equal each other. So what we're trying to figure out is whether or not the true means could actually equal each other based on the evidence and the data that we collect. Again, we have a null hypothesis that one minus another is going to equal to delta, and we're going to set that delta in this particular case equal to 0, so that what we're going to be testing is whether they're equal or they're not equal. So now that we have completed our analysis of the two mean hypothesis test, let's go ahead and go back to our hypothesis plan and kind of review what kind of decisions we're going to need to make during the hypothesis process. So the first thing we need to do is choose our null hypothesis. At this point, we've worked with the one mean hypothesis test and the two mean hypothesis test. The next thing we need to do is choose our statistic. Are we going to be using T or are we going to be using Z? And it's going to depend on what the N is. You can also think about it in terms of what the degrees of freedom is. So once we know whether we're using T or Z, we can go ahead and choose what our sides are. So if it's one-sided, we're going to have a critical value that just has an alpha on it. If it's two-sided, we're going to have a critical value that has alpha over 2. Now, at this time, we're also going to have to choose what our our alternative hypothesis is. Okay, so what do all these decisions get us? Well, choosing your null hypothesis is going to help you determine whether you're going to be using this column for your alternatives or this column for your alternatives, right? And the Z or the T is really going to make a difference once we get to pulling out what the Z critical value or the T critical value is, and also pulling out what equation to use for T calc. If it's one-sided, it's going to help us determine what is the critical value, because it's going to be different depending upon whether or not we have Z alpha or Z alpha over 2. And the alternative hypothesis is going to help us decide what is going to be our conditions for rejecting the null hypothesis. Okay, so this is going to be step 1. This is going to go into step 2 as well as 3. This one's going to go into step 2 and step 1. This one is really just going to show up in step 2, and this one is going to show up in step 2 as far as the reject the null hypothesis. But you can also use this to help you with determining the alternative hypothesis, which is going to be step 1. Alright, so then we get to the equations. This is all coming down to whether or not what equation we use for Z calc or T calc, and it's going to depend on whether or not what the null hypothesis is. So we have one set for a one mean hypothesis. We've got our Z and our T, and then in terms of our two mean hypothesis test, we're going to either do unpaired or paired. So we've got our unpaired right here with our T and our Z, and they look quite similar. The only difference is that we'll have to calculate a degrees of freedom to go with our number that are in our first data set and the number that are in our second data set, and we'll use that in our T critical calculation or estimation. And then in the two mean test, we actually care more about the difference between the two versus, and so we have an average of the differences versus the difference between x1 bar and x2 bar. And then on the bottom, we're going to have the variance of the differences as well. So you can kind of see that this one looks a lot like this one in that way. Oh, and don't forget that the assumption that we're making is that we're assuming unequal variances. That's the, yeah. Well, that's all I have for this 2 mean mini movie. I hope it was helpful.